Thank you, Matteo. So I know there was a poll this morning. Does anyone actually need me to speak in English, or do I switch to French? Raise your hand if you need me to speak in English. Otherwise, maybe I'll do it in French. Nope? I don't see your hand. No. OK. Alors, je vais faire en français. OK. All right. I can do it in English. That's fine. That's totally fine. All right, then. Hello, everyone. My name is Raphae Pinson. I work as a solutions architect at Isovalent, a company specialized in eBPF, based in the US and Switzerland, essentially. Oh, and it's this. So this is where I press the button. Yes. So who am I? I work for Isovalent. I'm a solutions architect working essentially on Cilium in France, which means I work quite a bit with Kubernetes, which is linked to the CNCF. So certified, CKD, CKS, and I actually co-organize a meetup in Romandie, in Lausanne, based on cloud-native technologies. And in the past, I did quite a bit of Puppet and Terraform, but now I mainly focus on Kubernetes. So what I want to talk about today is open source standards and technical debt, and mainly technical debt. It's not going to be a theoretical talk about technical debt and all that it is or is not. It's going to be a bit more, let's say, practical about things that we can do to reduce technical debt. So I'm going to talk about all this. Technical debt, standard instability, coupling and immutability. We'll talk about diluting the technical debt in human ways. This is DevOps days after all, so it matters. Haste versus speed, and choosing the right technology. So first, what do I talk about? What do I mean when I talk about technical debt? Well, not everybody agrees on what technical debt is. Some people prefer to call it, software erosion, software decay. I'm not going to talk about this in detail. Essentially, that's the idea that you have an accumulation of small decisions that accumulate with time, right? Who here likes to clean their house? Oh, there's one here. Okay, we need to talk. I don't like to clean. I don't like to tidy. But let's face it. If I don't clean too often, things pile up, right? And then at some point, I have a friend coming for dinner, and well, instead of just cooking dinner, I'm just going to spend 2 days cleaning the house, tidying up everything, mowing the lawn, everything. And that's the idea of technical debt. All the things that I didn't do accumulate, and at some point, there's a price to pay that is higher than it should be for small things, which is inviting someone for dinner. I actually need to redo the whole house, maybe change house at some point, if it gets really bad. And this can evolve very slowly from many small changes. It's hard to monitor. Sometimes you don't even see it until it's time to actually pay for all these things that have accumulated. And what does it look like when it's time to pay? It looks like this. So you have your system that has evolved maybe slowly, right? I call it a stuck system. It's usually not exactly stuck. The small features coming in. Maybe you're backporting some things, changing some configuration. But the state of the art has evolved much faster than your system. And at some point, you will need a feature that you can't implement on your own. You will need to get back to the state of the art because that feature is only available in the latest version of the software you're using. Or maybe even worse, you have a security issue, and the only way to solve it is to upgrade. And then you find out that if you upgrade, you need to redo the whole architecture of your software. And it's going to take 6 months. And it's a security issue that needs to be fixed yesterday. So that's the problem. So how are we going to get rid of this? How are we going to avoid accumulating technical debt so we can actually move in an agile way when it's time to move? So first, I think it's kind of obvious that technical debt has to do with standards. It's the idea of the state of the art, right? If you stay up to date with standards, then you should be fine. You just need to follow where the technology is at this point. And very often what we see in a lot of places, and I've seen this in a lot of places doing consulting, is where do you put the line between standards that are acceptable for you and standards that you don't really accept? And you typically see this with things that are easy to code, easy to implement. The line is usually at, if I can do it, I don't need anyone else to do it for me. So in a lot of DevOps / admin environment, the line is the DSL, let's say. So like Puppet or Terraform, very often teams are tempted to make their own Puppet modules, their own Terraform modules. Why? Because they know how to do it. Doing the provisioner, the provider for Terraform, probably not, because that's Go code. We're going to rely on the community. But when it gets to using the DSL, making modules, I can do it, I'll do it. So that's the whole idea of non-invented here syndrome. I'm going to make it on my own because I can do it. So the more technical the team, the more likely you are to actually have more NIH, more not-invented here syndrome, because we can do it. So we can reinvent the wheel if we want to. But the thing is that it can cover you for some time. And at some point, you'll need a feature that you're actually not able to implement. And at this point, you're going to pay the technical debt because you need to switch to a product that has this feature. And that means you need to re-architecture your whole system in order to use that standard. So you need to pay for this at some point. It never pays off on the long term. Another thing that we saw is lacking behind standards. So typically I think it was 6 months ago, in September last year, feels a lot longer, I was working at Camp to Camp with, they have a stand out there if you want to see them. And we were hit, I don't know if some of you were hit by this, by a deprecation of the DXT X3 root certificate. Does anyone know what this means? what this is about? The X3 CA was used by Let's Encrypt for many years until Let's Encrypt had a CA certificate that everybody trusted that was in all web browsers. And so for years, what happened is that the certificates that were distributed by Let's Encrypt were doubly signed. They were signed by the X3 certificate, and so the X3 CA, and the Let's Encrypt CA, in case you had an old system that didn't trust the new Let's Encrypt CA. And then at some point, the X3 CA actually expired, and that was in September last year. And what it meant is that operating systems that didn't have the new CA certificates would stop trusting the Let's Encrypt certificates. However recent your Let's Encrypt certificates were, and usually they are because they're renewed automatically every 3 months, they would stop being trusted because you didn't have the CA for the new certificate, for the new CA. And we looked into this at Camp to Camp. We're like, we're safe. We have recent OSs. We're totally fine. One thing we didn't consider is that we were using Rancher 1.6 at the time, and Rancher 1.6 had containers that were based on Ubuntu 16.04. And the result is that the containers didn't have the CA certificates. And our whole Rancher installation was based on Let's Encrypt certificates. And so the containers stopped trusting each other on that day, and the whole platform went down. And the main reason was everything was fine, everything was working, but we were lagging behind. And fortunately, Rancher actually published new container images with the certificates included. But besides this, we would have had to redo the entire architecture and switch everything else to Kubernetes, for example. We had started switching to Kubernetes at the time, but we still had some workload on Rancher just because of this certificate expiration and because the technology we're using was obsolete. So using obsolete technology can lead you to situations where solving a simple problem, I'm missing a certificate, actually leads you to redo the entire system. So it links to standards, and how a standard links to open source. Open source is, I think, very important in the context of DevOps, right? And for a lot of companies, open source is nice, it's free, we get free software, that's cool. I think it has a very pragmatic reason as well. There's very pragmatic reasons to contribute to open source and not just use it. Very often we think, okay, we're going to contribute to open source because it will be maintained by the community and maybe there'll be new features. I think this is actually a subset of the tech debt issue. Let's consider this. I have a need in a software, right? When I talk about standards, I'm not talking about changing the standards of the internet or things like this. I'm talking about a standard in the sense of what people use. What does everybody use, right? So let's say you use a tool and you're missing an option in that tool. You're missing a CLI option, for example. You could say, okay, well, I can do a workaround around this, right? I can write a script that will work around this thing, and at some point, there will be this option available. But the first thing you should ask yourself is, well, does it already exist? Maybe if I update the tool, the option already exists. Maybe it almost exists, right? Maybe if I check In the GitHub repository, there's a pull request there, and I just need to put a little thumb up and say, hey, how is this going? Can I help with something, to make this happen? Because I need this feature, and then it will be in the next release. And you will just be able to sync to the new standard, which will be the next release. If at this point it doesn't exist and you haven't found any trace anywhere, you should start talking to the community and say, does anyone else have this need? Because, let's face it, we all have the same needs. We're all using computers and we're doing pretty much the same things, right? So if nobody else needs that thing, you need to question, am I understanding my problem correctly? Maybe if I think of the problem in a different way, there is already a solution, but I just need to think out of the box. If the need is valid, and you're actually the first one to implement it, that can happen, right? Then if you start implementing it on your own, on your site, and keep it for yourself, at some point, if that need is valid, someone else will implement a solution to fix that thing. And this thing, at some point, will end up in the standard, in the open source tool, in the other tool, whatever that is, and you'll need to catch up with this. So you're accumulating technical debt because you'll need to migrate to the new standard at some point. If you actually contribute to the open source product on the other side, you're building the standard. You're saying this is the new standard, and if anyone else wants to do the same thing, they'll use your implementation, which means instead of having technical debt, you're actually ahead of the curve, and you're building technical debt for others, but that's their problem, right? So it makes total sense to contribute these things, to keep ahead and to keep up to date with the state of the art. Because again, the closer you are to the state of the art, and the less you'll have to pay the next time you need to sync with the state of the art. So it's the whole idea of either you follow the standards or you try to influence. I'm not talking about building standards, being the standard. I'm talking, contribute to the standards in a way that it will help others and it will also help you avoid technical debt. So what we see as well is that technical debt is very linked to coupling. So what do I mean by coupling? I mean systems that are tightly linked together. About 15 years ago, I was working as an Ubuntu developer, working on a distribution. I don't remember exactly which one it is. And about 10 days from release, I was working on KDE, integrating KDE, so in Kubuntu. Some people might still use this. And 10 days from release, we realized we couldn't print on KDE. That was pretty bad. And we looked into it, and we realized that just a few days before, cups had been updated. So the printing component had been updated to a beta version. And we're like, who did this? Why? This is 10 days from release. You don't do this. It turned out it was the GNOME people who had done this because, as you know, Ubuntu is released with GNOME so that you have the latest version of GNOME released on the day that GNOME is released. And the new version of GNOME required this beta version of cups. But Ubuntu, KDE did not support this beta version of cups. And so we were unable to print on KDE, but the GNOME people said, yeah, but if we don't update cups, then we can't print on GNOME, so what do we do? And distributions, Linux distributions are a typical example because they're using shared libraries for lots of components of very tightly coupled systems. You update a library because your camera doesn't work with your Linux distribution, and all of a sudden you don't have Wi-Fi anymore. And you're like, oh, great. So what can we do to avoid this? We need to use loose coupling. We need to decouple the parts of the systems. So typically take a monolith. In a monolith, the parts of the system, the components are tightly coupled, and as a result, the depth is tightly coupled. You touch a little library at the base of the monolith, you have no idea what you're going to break. And so that means that different components that use the same library are stuck together. And if you need a new functionality in a small library for one component, you need to reconsider the whole thing. So by decoupling the components of your monolith, it can be microservices, but just the fact of decoupling. I'm not a microservices yet at this point. You will actually decouple the depth as well. What this means is that you'll be able to control the depth of each component separately. So two components might be using the same library, but one might be able to actually update the library while the other uses the old version of the library because one needs new features and the other one is not compatible yet. So decorrelating dependencies and having loose API between the components so that you can actually update the components separately without breaking the whole system. And what you achieve with this also is distributing the technical debt. Let's talk a bit about immutability and how it's linked to this. So what I mean by immutability is systems that need to be entirely replaced whenever you change something in them. So in our day and time, that's typically containers. Though you can achieve immutable infrastructure using VMs, for example. And we've seen a progression towards immutable systems with the years. Immutability is saying, my car is dirty, I need a new one. So that's kind of extreme, right? When you talk about physical objects, because it means trashing physical object and replacing with a new one. But 20 years ago, we started having VMs. And all of a sudden, it became perfectly fine. I can trash a VM and start a new VM in a few minutes, and it doesn't cost much more. So it's actually doable, which means I can have a golden image of a VM. And if I need to change anything in that VM, I'll just make a new image, turn off the old VM, turn on a new one with the new image, and I'm done. You can actually roll out entire applications this way in the cloud by changing, let's say, your AWS AMI, roll out 30 new VMs, change the load balancer, turn off the old VMs, and you're done. This works if your system can be managed this way with immutability. On the other hand, if you have systems that usually are quite coupled, you'll have to rely on mutable systems where you will make the system evolve with time, typically using automation such as configuration management, right? So CF Engine, Puppet, Chef, Ansible, and so on, and make the system evolve with time. But you never really know if you restarted from scratch if your system would be exactly the same. How does that help, actually? So immutability can help because you're constantly making changes and restarting the system, replacing pieces of the system. It encourages a decoupled system because you don't want to rebuild the whole thing from scratch, the whole monolith from scratch. So it actually encourages decoupling so that you can replace small pieces of the system, small components, one after the other. And because it encourages coupling, like we saw before, it will encourage the distribution of tech debt. Also, what it does is that every time you have a virtualization and a decoupling from the underlying infrastructure, you're actually pushing the tech debt down to someone else. It still exists, but it's managed by someone who is specialized in the system. When we started using VMs, for example, and having cloud systems, whether public cloud or private clouds, we actually pushed some of the tech debt down. Because now, all of a sudden, I care about my VM, but I don't care about the physical layer anymore. It's not my problem. It's the problem of the person that manages the cloud. And now I'm using containers, I'm using Kubernetes. I don't care about the OS anymore. You can use whatever OS, whatever kernel, it's not my problem. I'm not managing this part, I'm just focusing on my container. If you switch to functions as a service, serverless, all of a sudden you don't even care about the container technology anymore. It's not your problem. So what happens is that you're delegating some of the tech debt to someone else, and you just care about the API. And this API is not strongly coupled with your application in such a way that there is a standard. If you follow the standard, you know you'll be able to deploy your function, and everything else is someone else's problem to keep up to date. This is typically the example of public cloud. I mean, we're paying public cloud because they're providing VMs, they're providing services, and so on. But this is not the only thing we're paying public cloud for. We're actually paying these people to manage a lot of our technical debt. When I'm using Kubernetes as a service, I'm also paying for Amazon, Google, or Hedora, or whoever else to manage the whole stack under Kubernetes and keep it up to date, so that if there is a new feature that is required, if there is a security issue, I know that they have the problem of actually going back to the state of the art, and it's not my problem. It's part of the contract that I care about my application, they care about the technical debt that is under my application. There is a little thing about this where we're not removing technical debt, right? We're just giving it to someone else and paying for someone else to do it. That's one thing. And the other thing is that you're still building technical debt depending on how you use cloud APIs. So if you link too tightly to specific cloud APIs, let's say you take an RDS database on Amazon, for example, well, you still link very tightly to Amazon. It won't be easy or even possible to migrate your database to another provider because you're tightly coupled with this provider specifically, which is why Kubernetes is great, because if you use standard Kubernetes features, then you have a standard which allows you to migrate your workload between different providers because it's standard. So this coupling problematic is linked to tech debt, but it has an influence on people, actually. And we like talking about people because this is DevOps days, right? This is important. People are at the core of what we do. There is this book that I strongly recommend called Team Topologies. Can I point with this? No, I can't. Team Topologies, I don't know if anyone knows it. It's a great book, and it builds on a law from the 1960s that for many years not a lot of people talked about and has become very prominent now that a lot of people talk about microservices and agility and so on, which is Conway's law. And what Conway's law says, sorry, I'm going to drink a bit. That's better. What Conway's law says from the 1960s is that the architecture of a system is strongly influenced by the organization of the teams that produce this system. And it's not a matter of choice. If you have your whole team in an open space, working however they want, communicating however they want, they will build a monolith. And you're like, okay, but people have a choice. They can do whatever they want, right? But no, this has been verified many times over. If you put everyone in one room and they work without communication channels specifically set, they will build a tightly coupled system, and it will be impossible to untie things because they can talk and communicate however they want. The communication patterns and the organization of the teams models the software you will produce. It doesn't mean you need to have people in separate rooms, right? What it means is that you need to have communication channels that mirror the architecture of the software you're building. So decoupling software means you need to decouple teams. It means you need that if two components of a software need to talk to each other with a given API, this API needs to be reflected in the way the teams are organized and the way they communicate. There needs to be a communication pattern that mirrors the architecture you want to have. What this means as well is that the depth will be distributed in these teams because the teams will be responsible for one or two components in the whole software. They will own the depth of this component, which has been decoupled from the rest. And if you consider a monolith, understanding the depth of a monolith is extremely complex. I don't think anyone in this big open space that makes this monolith can actually comprehend how complex it is and what will happen if we upgrade this library at the base. But if you decouple the systems and each team is responsible for one part of it, then each team actually can comprehend the tech depth of their own component and actually manage it in a proactive way. And what it means as well is that if they can understand the depth of their component, it will also distribute the mental load between teams, which is also a very important point in team topologies. The mental load of a team is how much a team can manage mentally in terms of what needs to be done in terms of features, instead of maintenance, in terms of technical depth, and so on. And so if it becomes comprehensible, then it means the team can actually tackle this problem and make sure that their component stays up to date in the system. Obviously, there is still the problem of the whole architecture that needs to be up to date with state of the art. That's the problem of the architect, right, of the solution. But distributing this task means everyone has some concrete tech depth to manage and can do it. Doesn't work anymore. I can't pass slides. I'm going to go here. Is it stuck? Help! Someone is using a Mac, so help.
What's happening?
I don't know. It doesn't work. It seems stuck.
I need to try now?
Yay! Thank you. Was there anything else? No. Okay. So more haste, actually less speed. In a lot of companies, the way state-of-the-art is managed is let's make a big project to move to the new thing. This project will take 5 years, and then probably it'll be 2 years late. So let's say 7 years, right? And then once you get there, maybe you reach the specification you made 5 years ago. So you're definitely not at the state of the art. It might not matter in terms of features, but it might matter in terms of security. Because when you have a security issue, what matters is how close are you to the state of the art that you can actually reach the state of the art whenever you need it for security reasons. So that's typically the Hare approach. Let's make big jumps. We don't care if we're late because we're fast. We can reach the new state of the art quickly because we have a lot of horsepower, so we can do it. The tortoise approach, on the other hand, is usually slow, but it's steady. It means that everyone has their own technical debt to manage and will increasingly, steadily, day after day, try to keep up to date for their own thing, and the whole system tries to stay up to date. It's actually much more efficient in a lot of cases. And this actually links to the 3 ways of DevOps, right? So as a reminder, the 3 ways of DevOps are flow and system thinking, amplify feedback loops, and culture of continual experimentation and learning. So if we look at the first one, usually we think about developers working with ops. So typically not, throwing the software above the wall and that's it, not my problem anymore. It works on my laptop, not my problem. So typically in this case, it can be, decoupling the software architecture from the underlying infrastructure. Because if the software is too linked to the underlying infrastructure, then whenever the operations need to update the OS, for example, they won't be able to, because the software strongly depends on features of the OS. Containers help a lot with this. I don't depend on the OS anymore. I just depend on having a container engine, which means that I know in my Kubernetes cluster, usually, that operations are pretty much free to update the nodes and it won't impact the applications. There might be some cases where it does, which is why the amplify feedback loops are really important. It means that operations will go back to developers or ideally be involved in the architecture of the software to say, wait a minute, what are you doing here? Is actually adding a strong coupling between your software and the underlying infrastructure. We know it's going to break in 2 years when we upgrade. We don't want to do this because we know that in 2 years there won't be any budget to redo your whole architecture. So make it so that I can upgrade my Kubernetes cluster in 2 years without an impact. Think about it now. It can be proactive, or it can be whenever this happens, that operations will go back to developers and say, change this. We're going to build tech debt. It needs to be changed. And obviously the last one, well, if that doesn't look like a tortoise, I don't know what does. It's moving slowly. It's moving steadily. It's a culture of continual experimentation and learning, which means slowly, steadily trying things, trying to get closer to the state of the art, looking for the state of the art. What is the new thing that I can try to see if I can keep up in a slow way? Not like in 2 years, not in 5 years. Now, let's try to build things, move a little bit forward so that I'm not too late whenever there is a jump to make. So obviously this means you also need to know where you're going, right? It's kind of obvious that if you choose a technology today that will be obsolete in 2 years, you'll have to switch to something else. If you can have let's say the nose, to know which technology is still going to be valid in 10 years from now, and you bet on this technology, well, you'll have less to catch up to. So think about what is a technology that will last and that you can build upon and not have to rethink your whole system in 6 months from now. And So when is the right time to adopt? Well, a lot of companies tend to be on this side, right? Early majority to late majority. And the result of this, it's not a judgment, right? The result of this is coming down to a Hare approach to the race. Why? Because when you're late to adopt a technology, you're typically the one running behind, which means you need to make big jumps. And when you make big jumps, you're never up to date. Well, being an early adopter is clearly more dangerous. But it's more of a culture of continual experimentation and learning, right? If you're an early adopter, you're lagging less behind, and so it's easier to catch up, and so there's less tech debt to pay on the day that you need to pay it. So it makes a lot of sense, actually, not necessarily to be an innovator, that's not what I'm saying, but to adopt technologies early, not necessarily in production, but to be ready enough to adopt them that you don't lag behind and have to make big jumps that are pretty much impossible to do very often in a timely manner. So we've seen that there's actually 2 conditions I talked about here. Again, this is not exhaustive. The idea is not to talk about tech debt in a very theoretical way, but two things here that stand out from what we've seen is stability. We want a standard interface, something that will pass the test of time, something that will last, that you know you can rely on in time and won't have to change to redo the entire architecture in a few months or years. And loose coupling is actually a very important point. If you're not tightly coupled to a technology, it means you can easily change, you can easily upgrade some parts, and you can delegate your debt between the teams, you can delegate the load, the mental load of this debt, and you can change the configuration of your software much more easily. You can change the architecture of your software because you have loose APIs, and so things can change without changing the functionality of the different components. I'm just going to take an example. I'm obviously biased in this because I work in the Cilium project. But here's an example with a technology that's pretty interesting in the Linux kernel, which is eBPF. eBPF stands for Extended BPF. BPF is the technology that probably most of you have used because it's used in TCP dump. This is what allows you to observe what's happening in the kernel as far as network flows go. And eBPF, Extended BPF, extends on this and allows you to actually inject small programs in bytecode in your kernel that will get compiled, verified, and compiled into machine code so that they are actually extremely performant. And then you can link the small programs, a bit like callbacks, if you will, to events in the kernel so that whenever there is network traffic on a network interface, for example, or there is, let's say, a file that is read or written, or there's a process that is executed or stops being executed, you can fire up the small programs. And then these programs will be able to write to what we call maps, which are structures that they can write and read from, and that programs in user space can also write and read from, so it allows to communicate between what's happening in the kernel, the small programs in eBPF, and what's happening outside of the kernel. There's lots of applications to this. You can apply it to observability, for example, because you see everything in the OS, literally everything, because you're in a kernel. Everything goes through the kernel at some point, right? So you can observe processes, you can observe network, you can observe any kind of thing in there. C group stuff, namespace, C group changes, and so on. You can apply it to security, obviously, because you can observe all these things. You can make alerts, and you can even react actively to what's happening. For example, if you see that any process is actually writing etc password or etc shadow, you can say kill that process if it's in a container, for example. You can apply it to network, and this is typically what is done in the Cilium project, where you can bypass stacks such as IP tables or even TCP/IP by capturing the packets that come out of a network interface using eBPF and rerouting them using eBPF again, or rewriting them outside of the machine. And you can do tracing and profiling again, because you see everything going through. You can dynamically gather information and typically export this to, let's say, open telemetry, for example. Why is this interesting in the context of this talk? Because we have these two conditions here. We have stability. This is based on very stable APIs, the kernel. What's more stable than the kernel in your OS? You know this is something that is staying around. You're not going to get rid of the Linux kernel, most likely for the months to come, probably years, right? I'm talking about Linux, but actually eBPF is also being ported by Microsoft to Windows, so even Windows might have eBPF soon. And loose coupling. Why? Because this is kind of magic. It looks into the kernel and it sees everything, so there's no instrumentation of your applications, which means you don't need to change your application, and so you don't need to migrate to new versions of the instrumentation library to get observability, to get network routing, to get security. It's just automatically provided because of the eBPF instrumentation based on the kernel. So how does it work, actually? The different use cases here, you have different projects. There's Cilium, there's Falco, there's Ktrend, there's more and more projects using eBPF to instrument their software. Usually they don't write code in C and inject them. There's actually SDKs to help with this that will allow you to write your code using Go, for example, and then inject this into the kernel using eBPF. So you get a verifier that verifies. There's lots of conditions. You cannot inject whatever you want into your kernel for security reasons, right? You don't want to crash the kernel. That's usually a bad idea. And here, what you're doing is actually adding functionality to the kernel in runtime. You don't need to recompile the kernel. You don't need to reboot the machine even. It's runtime. So you will inject the code into a kernel. It gets compiled using a JIT compiler. And then this code can communicate using maps. And then the OS runtime will run it. And then you can get tracing, profiling, observability, everything I was talking about before. So some examples of products that use this. So typically Cilium. And how is that interesting as far as technical depth is concerned is that you can get a simpler architecture, for example, by get rid of sidecar proxies for service mesh. Hubble will give you a lot of observability for networking without needing to instrumentalize your applications, export them into Splunk, and so on. And Tetragon, that is a new product, will allow you to observe, export kernel events, and maybe act even on these events. So this is more if you want to know more about eBPF. Again, that's just an example, but the principle is really look for stable systems, stable APIs that will last while you don't need to migrate to something else, and loose coupling that will allow you to move the different components without having to rebase your code. So if I had a word of conclusion on this, I would say what matters is not the speed, really. It's the direction. Choose the right direction. Choose the technology that will allow you to still be on the right path 5 years, 10 years from now, hopefully. And then don't couple too strongly with it so that you can make incremental changes. Make sure that you distribute your depth, distribute your mental load so that it's actually manageable, and stay up to date by moving slowly and moving steadily and trying to keep up with the state of the art. Thank you. If there's questions, I welcome questions.
Thank you very much, Raphael. That's brilliant.